we move on, we all know how important it is to combine theory and practice in science and how great minds can help us understand the most complicated and elaborate processes of AI. Welcome to our next speaker, the Doctor of Mathematical Sciences and author of hundreds of research papers, Alexander Gasnikov.
Научный сотрудник, доктор физики.
Research fellow, PhD in physics and mathematics, rector of Innopolis, Alexander Gasnikov.
И сравнительный оракул. Ускорение и стохастический случай.
Acceleration and stochastic events. Hello, colleagues, and today I will be talking about the NIPS article published just this year. It is being presented as we speak. The article is about the comparative oracle, but basically this is something that AI literature often refers to as RLHF. You can see this here on the slide in the corner. And so let's begin. What was the motivation? The boom happened in 2022 with the publication of an article in May 2022 by OpenAI that described Instruct GPT. The article was called Training Language Models to Follow Instructions with Human Feedback. So this human feedback is a very important addition. When an LLM, using settings from some small number of hyperparameters, gives you an outcome and you compare it with an outcome of some other model with some slightly different parameters, it's very difficult sometimes to apply quantitative assessment to the texts. But you can say that you like this text, you prefer it to the other. This is called feedback. This comparative feedback, preferential feedback of humans. It is based on your preferences that you can apply to the outcomes. And this is unusual because the usual situation is you get the gradient of the function and you try to spot the minimal of a function based on the feedback. It didn't take long, because just a year later, oh, by the way, this article that I showed by OpenAI, it was a harbinger of what happened in November 2022. It was a huge publication about ChatGPT by OpenAI. The word open sounds a bit ironic, but nevertheless. A year later, at another NIPS, another article appeared called Is RLHF More Difficult Than Standard RL? The highlighted sentence, if you read it, you will see that the answer is roughly along the lines of, no, it is not more difficult. In simpler terms, if you're looking at an RL problem, a reinforcement learning problem, if you are considering the usual reward system or the loss function, which is set, well, that's one approach. Another approach is when it is not set, and you can only compare whether this output is better than the other or worse, but not qualitatively. You just say, but not quantitatively. You just say it is better or worse.
So, like, the second feedback is kind of limited on the one hand. On the other hand, it helps you to train with the same quality. Yes, that's of lower quality, that's slower, but, you know, logarithmically speaking, it's not that bad, it's not worse. That was a result that was achieved a year ago with the RLHF class of tasks. If we take general optimization, task optimization classes, we have to understand what task do we want to resolve, what problem do we want to resolve. We have a function, and this is the we need the stochastic optimization, and we have various options of putting the problem. We have x and y dots, and as a response we have a sign, -1 or 1, the digit. Moreover, it can have some noise, so it is possible. So f from x minus f y will have some noise. I'm not going to talk about that in detail, but I just put it on the slide to make sure that you understand that we can do these things, and our paper actually talks about that. We have estimations on the possible level of noise, permissible level of noise. I'm not going to talk about that in detail right now. The second concept is related with the feedback or the oracle. That does not give you the value of the function, but give you the value of the function on some implementation. So you can sample f from x with psi and compare f x psi with f y psi. And we are going to look into various problems so that you understand that it is actually applicable. On summer 2023, a physical technical university student, Andrei Krasnov, reached to me, and he said that he is making a smart coffee machine together with the other students of the university. The idea is simple. You set a couple of parameters, like the volume of the amount of milk and sugar that you're going to put into coffee. That means a proportion. And the person tests this coffee, changes the parameters, and tastes the coffee again, and gives the feedback to the coffee machine to say whether they liked the coffee or not. Now, the task was the following: how to make sure that you select the best coffee for this particular person while minimizing the number of attempts. This machine can learn based on different people. Every person with its own psi, right? One person is doing the labeling here. They compare it, and there's another person. He also compares it. He wants to fine-tune, we want to fine-tune the model, the coffee machine for an average person. This is the stochastical problem, and the results were as follows. The results are complete, I would say, in this way or another. We thought that it was pretty simple, and there was a request from Quantic journal, fantastic journal, by the way, excellent journal. It's really a fantastic journal for kids. Together with Nikolai Andreev, with the same one that I talked about in my presentation. So we wrote an article on how to find the best chocolate bar, the most tasty one. And we wanted to test how much strawberries there were in the Sber-produced chocolate bars, but Mr. Vedyakin and Mr. Niznamov gave me a lot of chocolate bars like that. So I was going around the schools and I was giving out these chocolate bars. Obviously, the children were very excited. But anyway, I'm going to tell you how do you make a smart chocolate bar. We will start with an oracle. You have to find the combination of the cocoa beans to make sure it's not that bitter, but at the same time it shouldn't be too sweet. Right, so the amount has to be optimal. We take 2 chocolate bars. You see the first diagram here on the left, and if we have a general understanding on how the tastiness function looks like, it seems that this is this function, and we give to an expert the possibility to taste various chocolate bars with various with the various share of ingredients, and we had the raspberry there. Now, if we take these dots in the like 1/3, then 1/3 and another 1/3, after the iteration, we'll have a 2/3 that will be left. So we take a section nearer to the dot that is smaller. We remove this section and we have this yellow section that remains, and the same applies to the next stages. We see that we divide the section into 3 and do the same thing. We will find the epsilon solution after logarithmic calculation. In terms of the logarithmic dependency, it's optimal epsilon-wise, but it's not really optimal in terms of the foundation of the algorithm. You can do a better thing. The golden ratio method is here on the slide, GRM, golden ratio method. So the idea is pretty simple. We should not remove the dot that remains. We have to use this dot and to add another one. And based on this assumption, we have to select a new dot so that the section that we remove, that removes a dot, does not change anything, and on the remaining section, remaining dot can be used as a base to continue the calculation in a similar way. So there should be similarity, and based on this similarity, we understand that the relation between these dots, especially the dot on the right, should be F. That's a golden ratio. We're talking about the green section. The ratio of the yellow section to the red section should be F as well. That's the golden ratio method. I'll speed up a little bit to have a Q&A session. We had a 2D generalization. It's a very beautiful one. So the thing I talked about was for the school kids, how to select the best chocolate bar. Now we have a 2D generalization where we have 2 variables, 2 ingredients. It will be published in Quantic Journal very soon, but I can take some pictures from this article. We have the problem of optimizing a 2-variable function, and the height level is 3 kilometers, and the section that we have for the surface of 3 kilometers is reflected by these multiple levels. We take the square. We have a vertical line that divides the square into rectangles. We try to find the maximum on the section. We find the dot on the drawing. We go to the left and to the right a little bit. We see where the value is larger. The section with the higher value remains. With a smaller value is removed. Then the rectangle is divided by 2. We have this section in the middle. We try to find the maximum value there, and the same goes again. So this is how we do it, and we'll have this logarithm in this square. 3D and 4D is also possible here. But it's not really good to generalize it like that, because the factor of the algorithm will grow together with the factor of the space, and if you achieve 10, then it will not be practical. Now, what is the idea I will use gradient method to show you how it's done. So the initial target function is the models. We replace the complicated function with a parabolic model. What is a parabolic model? We take a Taylor row, replace the Gaussian function with a spherically symmetric function. So we make a top-down assessment of this Gaussian to have this function. So we're building the measurandoms here. So it's measuranda that is built based on the Taylor row distribution. The geometry is pretty simple. We are moving to the minimum of this parabola. This is the gradient descent method. So we replace xk with the target function, and we go to the minimum of the paraboloid of the rotation. That's the idea of the gradient descent that you know about. Now the idea of the method that helped us to get the result. The random coordinate descent, a paper published in 2012. We select the coordinates, different policies to select the coordinates with different level of probabilities. This is just this paper that I exemplified, but there are other papers. Our task is to resolve the task of simultaneous search along this coordinate. But there's an interesting thing here, because if you look at the Nesterov article, we were looking at the step 1 by L that I talked about. And the dot that we had to have in Nesterov method, that's the minimum of this rotation paraboloid. This is a parabola here, by the way. So our gradient method is where we take the dot that is the minimum of parabola, and it shows this is a better result, really, because if we try to prove something with Nesterov method, then we can prove it with the other methods. That's a pretty simple thing. That shows that we have this summarization, and we have a golden section method for this problem. But you have to make this 1D search with some degree of accuracy. Yeah, it's very hard to explain to you all what's under the hood here, but you have two 1D searches, and the idea was to find the component by component method that is not that is convergent, but not in an optimal way. So the accelerated method can be compared with the Oracle method. This coordinate method is delivering the results that are acceptable, but we change the Oracle. We change this movement through the coordinate with a 1D search. And that's this oracle that I've showed about. It needs to be proven. It's not really clear that if you can change the one gradient step with the 1D search, is something that you need. It needs proof. The main result is formulated as this one sentence, is that the oracle that I've implemented, this feedback from the human, are basically the same apart from the 1D search. 1D, well, search costs something. The logarithmic number of steps, and the difference of this logarithmic number of steps is the difference between solving a big problem and with the it can be compared with an oracle. So if you have a value of a function, find the minimum, that's one thing. And then you can ask for a function value in various dots, and it's going to be sorted in ascending or descending order. That can seem weaker, but it's weaker by a logarithmic number of times. Now, stochastic optimization, the mathematics here is even more beautiful. You see it on the screen. And here we introduce this method option with additional randomization. So we randomly select the EK direction on the 1D sphere. We select a step, ETK, in accordance to what is written here. Right, so this is how it's done. It's a Yuditsky-Polyak step. They explain why it's used in great detail in their work, in their paper. Then there is an important limitation, the additive noise. And this is a limitation. I do not know how to address that, but our noise is not focused on zero, because if the noise is focused on zero, it is very challenging, it would be very challenging to resolve a problem of seeing a difference between these two functions. Now, a couple of other lemmas that help to find this result. Now, the function that was introduced, the phi function, and this is a feedback from the oracle. This is this sign. We can understand it as a sign of this formula. If it's too small, if you look at the approximation. We can replace this and difference with the Taylor row. And to do so, the step should be much lower, much smaller. The smaller the step, the worse the method can be, the worse the conditions for using this method. So we take the step that would have this lemma proved. And these researchers made this kind of result, the convex optimization, the result of Polyak-Tsypkin. You can see that on the screen. It is about the gradient descent, but with an aggregate that we built based on the oracle that we have. So we have an oracle that gives us this difference, and we have to do something similar for the stochastic gradient descent. It's understood that it's very hard to get 100 as a gradient because you have this sign here.
But this lemma, or rather this last line you're looking at, is the step that we need to make to understand how the stochastic gradient emerges. If I take the mathematical expectation of the aggregate, the mathematical expectation based on the random function that I introduced with E, that's why I introduced the E. This is a non-trivial construction. That's the trick. I added this E randomization in order to use it to get the mathematical expectation and get the gradient, because otherwise I wouldn't be able to build it. This is completely out of the box thinking. So for this procedure, we can prove the convergence of the result, of the Polyak and Tsypkin result, where with the natural speed 1 by k-rooted will lead us to the convergence of the matrix. We can also divide it by k. We can divide the method step by k. I will go back to that in a minute. So you will get the correlation matrix with the normal distribution. An amazing idea. Polyak didn't think of it, or rather Polyak thought of it in a dream right before a seminar. So he thought that he could take an average of the point trajectory. He had a regular stochastic method. We are using it for a specific application. But in any case, he thought of the Polyak averaging, where we use the arithmetic average for the trajectory. And it significantly improves the quality of the matrix. Once again, the normal convergence, the same procedure, but when the outcome is the arithmetic average, the matrix turns out much better than the one we had before, thanks to the trajectory average. I hope you can see it well enough. I'll describe what you're looking at. The left is the Polyak-Tsypkin procedure and the convergence for our context, the oracle context. Then we see the distribution with the 0.1 scale. And then if we want to optimally select parameters, that's what I was saying, you can select the parameter as 0, the step parameter, then the distribution will have the scale of 0.1, of 0.0001. That shows how important the learning rate is and how important mathematics is. The effect is very considerable. And then we add the averaging effect. Once again, the mathematical function, the same procedure at the same time, but the output is not the last point, but the trajectory average. Once again, we are reducing, we are making the correlation matrix, in our case it's a 2D matrix, it makes us even more concentrated around the solution, around the output. There is a CPT, the output point has the distribution, the normal distribution.
Тем меньше, чем больше математики вы пытаетесь учесть. Мне кажется, что вот на таком примере
I think with this example, you can really see all these amazing things that were invented back in the 80s. That's it. The main point of my presentation is that we should be optimistic because an oracle like this performs pretty well. I'll be happy to take your questions. Alexander Gasnikov. Round of applause, please. Alexander, you are a virtuoso at presenting these extremely intricate topics and add some chocolate with raspberries to mathematics. And as a result, we are getting loads and loads of questions to you. If I may, I'd like to ask some of them. What are the key advantages that reinforcement learning with human feedback gives in model training? I would say that this is the future. I think going forward, when we use a huge amount of AI assistance, agent-based systems, we will be giving it feedback, what we like, what we don't like. We don't want to spend too much time thinking how we should quantitatively assess things. It's not efficient, even. Instead, we could just quickly assess whether we like something or not, just press the button and express our preferences. I think that's where the future lies. We will be personalizing the assistants that we'll be working with, and an oracle like the one I showed, if it has a good theoretical base, it will be making our lives easier, because with the feedback, the models will be getting fine-tuned just as quickly as with quantitative feedback, or even faster. It's just that with quantitative assessment and quantitative feedback, it's harder for us than just saying what we like or do not like. With the RLHF, is there a gradient descent for the distribution function of the gradient? When we're working on theory, usually scientists
но делают выпуклые случаи. И это не то, что вот мы так делаем, это общая практика. То есть, скажем, там статья Адам, да, там, ну, методы, которые...
try to illustrate their points with application cases. For example, they are selecting parameters theories for a
И, соответственно, говорится, вот смотрите, как здорово, вот смотрите, как
convex case.
Смотрите, какая оценка скорости сходимости, смотрите, как надо...
Look at this wonderful theorem, look at how you should select parameters, and then they say, well, let's try to apply this to actual language models, but there are no guarantees that it will work. It does work often, strange as it may seem, even with the parameters that are selected for the convex situation. They do work sometimes. Often, if anyone decides to underpin this with a theory, and nevertheless, it often turns out pessimistic. With our situation, we could get optimistic parameters. The answer is that with the cases that we theoretically have been studying, we do not encounter such regimes, so we haven't studied it in theory. That's how it is. Another question I wanted to ask, what are the risks posed by the stochastic approach to applying it in critically important tasks? The thing is that the stochastic approach is like the average temperature in a hospital. Maybe you like milk chocolate, I like dark chocolate. How do we marry the different tastes? It's not a trivial task. Same goes for wines. A sommelier may be tasting wines, selecting the best ones, and this is practically the task of when we're looking at the stochastic approach, we need to understand what is the human average, how do we select the representative sampling, because a typical sommelier is not a regular human being. If we gather a group of sommelier experts who will be able to label different wines, this wine will be very specific for specific tastes, for maybe a narrow demographic, not for the broader audience necessarily. So the question of ensuring this representative filling up, these C being indeed random representing the whole data set, I think it's a big problem, and it's difficult to figure out what the solution might be. And also the noise that is present, if it is concentrated well around the zero, the approaches that I presented are once again associated with complications because there is no good theory underpinning it. So I'm sorry for such a non-optimistic answer. Maybe another question so that I could give an optimistic answer? Well, there are a lot of questions about the future of AI in general. For some reason, many believe that it's engineering that will be developing AI, and a lot of people I respect do believe that it all lies in engineering. I do a lot of presentations and speeches, I talk to students and even school children a lot, and what I'm getting from them is that is this idea that there is great mathematics in the foundation of it and a mathematical viewpoint. So I believe the future of AI is in mathematics and evolutionary biology. You need to know mathematics and evolutionary biology to be developing AI. The fundamentals. Thank you very much, Alexander Gasnikov. You have also quenched our thirst for knowledge. When you mentioned wine, metaphorically speaking.